Hello, welcome back. In this lecture, we will learn how to perform linear regression using R. In linear regression, for example, simple linear regression, we are fitting our data to a linear model. For example, when I mean a linear model, in case of simple linear regression, I mean I have one dependent variable, say y, or sometimes you call it a response variable, and it is linearly dependent upon a independent variable, right, x. So, your linear model can be y equal to b into x, b is a coefficient or constant, plus a. In this lecture, I will start by fitting a blood pressure data, where the blood pressure is a response variable and it varies, we believe, linearly with age of a person. So, I will try to fit this age versus blood pressure data to a linear model of the form y equal to b into x plus a. So, let us do that on RStudio. So, I will be fitting my data to this simple linear equation y equal to a plus bx. A and b are the coefficient or constant, and we have to calculate those values a and b by linear regression. The first step of doing the linear regression obviously will be to read the data. So, let me read the data using read.csv file. I have a CSV file in my current working directory. The name of the file is bpdata.csv. So, I will read that data using read.csv function, and I will assign that data to a variable d. Let us check the data has been read, and let me click on this data d on environment pane and see what we have in the data. So, it is a 2-column data. You can see I have 30 rows, that means 30 observation, and the first variable, the first column is age of the person, and second column is the systolic blood pressure. So, we believe that systolic blood pressure, which is a response variable, has a linear relation with age. So, I want to perform the linear regression for that. But before going into performing the linear regression, I want to check whether the data itself has some linear trend or not. To do that, the simplest way to visually check the data, that means I will plot this data and see whether there is a linear trend between these two variables or not. And the second one that you can do, you can actually calculate the correlation coefficient between this age variable and the systolic blood pressure variable, and see whether the correlation value tells us whether there is a linear relation between these two variables or not. So, I will first draw the data. So, I will plot it as a sort of a scatter plot. So, I will use the plot function, and it will take multiple input, multiple argument. For example, age of my variable age will be my x axis, horizontal axis. So, I am writing d is the variable where the data is stored, right, the data frame, d $sign. So, I am and then putting age, I am writing age. So, I want the age variable of d, that is my horizontal axis, that is why it is the first argument. Second is sys.bp, this is the variable which will go in the vertical axis. So, d $sign sys.bp, this is my vertical axis. Then I want to label the x axis as age. So, I am writing x lab equal to age. I want to label the y axis as systolic blood pressure. So, I have written y lab equal to systolic blood pressure. Remember, all these are within the apostrophes, and then I want to use a red color and for those data point, and I want to use the circle. So, the shape of the data symbol that I have to use is denoted by this pch variable, and I have assigned that as 1, and cx, this argument I have set at 2. So, that will tell us the line thickness of this symbol, right. So, now if I plot it, before I plot, I will change the size of this plot zone so that it can accommodate. So, I have plotted, you cannot see anything clearly here. So, I will zoom it. Okay, I have zoomed. So, in the horizontal axis, I have age of the person, and the vertical axis I have the systolic blood pressure, and these circles are the data points, except a outlier here high, whose blood pressure is near to 20. Almost all data you can see there is a sort of linear trend, and it seems as if the blood pressure is slightly increasing as we age, as the person age with time. that is fine. So, that means the proposition that I will fit a linear model to this data is a right proposition. Now, I will check the correlation coefficient, or rather the Pearson correlation coefficient. So, for that I will use the function core, right. I will use the core function. So, core function will take multiple argument here. I have to define those two variables for which I want to calculate the correlation. So, I want to calculate the correlation between age of D and sys.Bp of D. So, these two are the variable, age and systolic blood pressure, and the method that I want this function to use is Pearson, because it can, this same function can use correlation between two variables using other methods also. So, I am saying method is equal to Pearson. So, if I execute this function, it tells me the correlation between age and systolic blood pressure, these two variable in my data, and it is a positive value and is equal to 0.657. So, that means there is a good positive linear trend between these two variables. So, going forward, we can go forward for the linear regression. To perform linear regression, I will use a very powerful function called linear model, or LM, right. So, LM function can do different types of, create different types of linear model, and I will go through one by one in this lecture and another lecture. So, I will use the LM function, linear model function, and I will use age as my independent variable or predictor, whereas systolic blood pressure will be my response variable or dependent variable. So, how do I define the model? Okay, I will call this LM function and I will give two arguments. Obviously, the second argument written here is the data. So, I am saying D is my data, data equal to D, and the first argument defines the linear model that I am creating. So, what type of linear model I am creating? I am creating systolic blood pressure is equal to a constant plus another constant into age, y equal to a plus bx. So, x is age and systolic blood pressure is the y. So, by writing this sys.Bp tilde age, this by this way I am telling the LM function that I want to create a linear model where the dependent variable is sys.Bp, whereas the independent variable is age. And the second argument, as I said, is the data. I execute that and take that value, the whatever output comes, and assign that output to this reg variable. I have executed. Now, I have to check what I have got by this regression, right. So, I will use the summary function to look into what we have stored in the reg variable. So, let me check the summary, and this summary tells us lots of things. For example, it will tell me the value of the coefficient, right, y equal to a plus bx. A and b are the coefficient, we want to know them, those are unknown to us. By regression, we want to find them. So, the summary of this regression data will tell me that what are the value of these two coefficients. At the same time, it will perform t-test for each of these coefficient and tell me whether these coefficients are statistically significant or not. It will also calculate the R squared, which is required to check whether the model is fit properly or not. So, I call the summary function and use reg as the argument, because that is where I have stored all the regression data just a few seconds back. Let me expand. So, here comes all the information given by summary. The most important part I will highlight here, the coefficient y equal to ax plus b. So, coefficient are a and b. So, the intercept a is 98.7 and the age coefficient for age is 0.97. So, that means my equation in this case is blood pressure equal to 0.97 into age plus 98.7. Now, once you have calculated this coefficient, you will obviously go for checking the R squared value, right, good to check the goodness of it. So, the R squared value is given here in this line, and it gives two types of R squared value. One is called multiple R squared, another one is adjusted R square. We have studied adjusted R square where when we were studying the multiple linear regression, Adjusted R square is not required for simple linear regression where I have only one independent variable. This multiple R squared is what we call simply R squared value, and I have, for this particular problem I have to check that value. So, the R squared value is 0.4324. It is not very close to 1, but looking at the data with the dispersion that we have and considering that it is coming from not a experiment in lab, but from a population data, is quite a reasonable value. And now I will check for the data for t-test. As I said, the LM function has already performed the t-test for each of these coefficient, and I will check the probability that is coming for each of them. For the intercept, this first line, look at the last column. The p is 1.28 into 10 to the power minus 10, extremely small. That means I can easily say that this intercept value estimated by linear regression is statistically significant. Whereas for the age, the coefficient is 0.97 and the t-test result, the p value is 7.87 into 10 to the power minus 5. Again it is very small. That means again the coefficient which is just before age, the coefficient for age is also statistically significant. Fine. Now, when you use the LM function, it automatically calculates do the ANOVA, but in case of a linear regression, simple linear regression with one independent variable, ANOVA does not make sense here, but that will be useful when I will use the same LM function for the multiple linear regression. So, that is what I have got from the summary of this regression result, and we are almost done with that. A few things that I have to check again. You may be interested to know the confidence interval for this estimated coefficient, right. So, I will calculate the confidence interval. To calculate the confidence interval, I will use a function called conf_int, right, and I will call that function conf_int, and I will give the reg variable which is storing all the regression data as one argument, and I will define the level of significance, and I am saying 95%, that means 0.95. So, let me clean it first the console a bit, and if I call this conf_int function, it will calculate the confidence interval for each of the calculated coefficient. Okay. So, it is saying that at the confidence level of 95%, that is 0.95 level, the value, true value of the intercept varies from 78.2 to 19.19. Whereas, at the same confidence interval, the age, the true value of the coefficient for age varies from 0.5 to 1.4. So, easily using this confidence interval function conf_int, I can calculate the confidence interval of my estimated parameters or estimated coefficient. Now, I am done with the regression. I have got the coefficient, I have done the calculate the confidence interval of those, I have checked that they are statistically significant. Now, the last step remains with me is to actually plot this regression line and overlay on the original data set, right. So, how I will do that? I will now overlay my regression data, the regression line that we can generate using the calculated coefficient and the coefficient for age and intercept, those values. So, what I will do? I will use the Abline function. Abline function add a line on the existing plot. So, Abline function, I will give this reg variable which is storing all the regression data as one of the argument. I want a blue line, so I am saying color equal to blue, and the line width or the thickness, if you say, is LWD, I have defined at 2. So, if I execute that, the line has been drawn, but let me zoom to see it clearly. So, now you can see this red are the scatter plot original data, and the regress line is this blue line. That is all, so simple. So, I have used the LM function to perform the regression, and then got the statistics, and as I am happy, I am plotting the data. Now, I will move into another example for linear regression, and that is one example that most of you working as a biology student or must be performing that type of regression regularly. That is for estimating the concentration of a unknown solution of DNA or protein. right. So, if you do some colorimetric or UV visible spectroscopy to measure the concentration of either DNA or protein, what you do, you create a standard curve. You have an experiment. For example, suppose you have known samples of DNA with different known concentration. You take a UV visible spectrophotometer and measure the absorbance of those samples, right, and you plot that data, perform a linear regression to get a standard curve, and then you use that standard curve to estimate the concentration of an unknown DNA sample using its absorbance. So, you must be doing that. So, I will show how you can perform the linear regression for that type of experiment using R. So, I already have a data set where I have taken different samples of known concentration of a DNA, and then I have measured the absorbance of that in 260 nanometer. So, let me first read that data. This is a CSV file called dna.csv present in my working directory. So, I will use the read.csv function to read that and assign that data to a variable called DNA. Let me show you what is the data I have. So, this is my data, concentration versus absorbance, right. So, I have the concentration in the first column and the absorbance in the second column, and I have 7 samples, and I will highlight one point. The first sample is concentration 0 and absorbance is 0. That is what is our usual practice. We take a blank and then we auto 0 the reading of my machine, right. So, by default, by this auto 0, you are making sure that the absorbance becomes 0 when the concentration of the DNA in the sample is 0. So, once I have that data, now I may want to plot that data and see how does it look like, right. So, again I will use the plot function and I will define the variables. In the horizontal axis I want the concentration. So, it is DNA, the $ and concentration, CONC, and then the vertical axis I have the absorbance. I want to label x and y axis by concentration and absorbance respectively. I want to use the red color and I want to use the circle and other things. So, if I execute this, I will get a plot. Let me zoom it to see how does it look like. Okay, this is usually decent plot for DNA absorbance that we do to create the standard plot. Now, I have to fit a straight line to this, right. So, to fit a straight line, that means I will do linear regression, simple linear regression. So, I will use the LM function, and by LM function by default we fit the equation y equal to a plus bx, and we estimate the coefficient b and a, right. So, in this case my model is absorbance equal to a, the intercept or a coefficient, plus b, another coefficient, into concentration. So, I am calling the LM function and I am telling it that create a linear model between absorbance and concentration, where concentration is the predictor or the independent variable and absorbance is the response or dependent variable, and use the data equal to DNA, and then you calculate all these things and store that data in the variable R1, regression data in R1. So, here I do the regression. R1 is now storing all my data coming from the regression analysis. Now, I will take the look at the summary of that. So, if I look into the summary, what I will get? I will get the value of the coefficient, the intercept and the coefficient, right, b, and also it will perform t-test, it will calculate r square, everything. So, the intercept is 0.018477, whereas the coefficient for concentration is 0.0147. And r squared value, we have to take the multiple r squared, just as I said in the previous example, and it is quite good, 0.9838. Now, let me look into the t-test result. For concentration, the p value is 1.13 into 10 to the power minus 5, quite a small value of p. That means the coefficient calculated here is statistically significant. But check the p value for the intercept. It is 0.088. That means even if I consider a cutoff of 0.05, then also it is bigger than that value. That means even at the level of 0.05, the intercept that I have estimated is not statistically significant. And as I discussed in the lecture on linear regression, that means from our linear model, we should remove this intercept, right. But there is another way of looking into this problem. which is more connected with what the experiment I have performed. Let me explain that. So, what experiment I have performed? I have performed a experiment where I have taken different samples of the same DNA with different concentration. I have measured the absorbance. And we know if I can make a sufficiently diluted solution of this DNA, this result should follow Beer-Lambert law. And I hope you remember the Beer-Lambert law. Just to remind you what is there in Beer-Lambert law. In Beer-Lambert law, the absorbance of the sample should be equal to L is the path length, into C the concentration, and in the beginning I have a constant term, right. So, A equal to eta into L into C. Now, that means A and C is linearly connected, but remember there is no intercept term here. So, the equation equivalent to this is y equal to Bx, not y equal to Bx plus A. So, Beer-Lambert law itself does not have an intercept term. Now, my whole experiment is relying upon actually Beer-Lambert law. That is why I believe concentration and the absorbance should have a linear relation. And the law itself says that there is no intercept term. That means I should never use y equal to Bx plus A form of linear regression in this case. I have to perform linear regression without the intercept. I have to tell my LM function that see there is no intercept here, it is y equal to Bx, right. So, that I can actually specify when I am using the LM function. How can I do that? That is what I have shown here. I am calling the LM function and I am telling the to LM function that model is absorbance and concentration plus 0. That means this by plus 0, writing this plus 0, I am specifying the function that see in this case you have to set intercept equal to 0. Do not estimate the value of intercept, right. And then obviously the data is equal to DNA on which I want to perform the regression. I performed it, and now let me check the summary of this by calling the summary function, and now I can check the values of the coefficients. Now, remember in this case there is no intercept, so only one coefficient is calculated, that is for the concentration, and that is given here 0.016, and its p value is very low, that means it is significant. I have the r squared value, right, and that is quite decent enough. So, that means now I have performed the regression properly. Now, I have created a linear model for my concentration versus absorbance data which follow Beer-Lambert law correctly, right. So, I have performed it. Now, what I will do, I will plot this regress line so that I can use that line to calculate the concentration of an unknown sample. So, to do that I will draw the line using the Abline function, just I have done in the other case. In this case R2 is the regression data set and I want a blue color with line thickness 2. So, here you can easily see this is my red circles are my data and this blue thick line is my regressed line, that is my standard curve. And just to remind you again, when we use UV visible spectroscopy, when we are using sufficiently diluted solutions, we believe that this experiment follow Beer-Lambert law. In Beer-Lambert's law, absorbance and concentration has a linear relationship, but in that linear relationship there is no intercept term. So, that means when I will perform linear regression, I should always remove that intercept term. And you can easily understand that if I do not have any intercept, when 0 is the concentration, absorbance should be 0, and that is what you have done when you have set the machine at auto 0. That is all for this lecture on linear regression. We have taken 2 examples, and in both cases we have used the LM function to perform the linear regression and then overlay the regress line on the original data set. That is all for this lecture. Thank you for learning with me today.